Dr. Andrew Gooley, and he's the Chief Scientific Officer for Trajan Scientific Medical, a global business with the headquarters in Ringwood. Over the past 40 years, Andrew has experienced a career in both academia and industry. His passion is mentoring the next generation of scientists and engineers and introducing them to the opportunities that industry can provide and the diversity of careers that are possible, from R&D, production, project management, quality, and marketing. In his commercial role, he's led multidisciplinary teams of engineers and scientists on a diversity of projects from omics, instrument development, through to consumables for chromatography for the global analytical science community. He was appointed as a University of Melbourne Enterprise Professor in Chemistry in May 2018. Welcome, Andrew.
Thanks, Brad, and hopefully that's all coming through okay.
Yeah, we can see and hear you perfectly. Brilliant,
brilliant. And thanks again for the introduction and, more importantly, the opportunity to present on exactly what you highlighted as my passion. The device, with a slight change in the format of today, that the device we're going to talk about is I'm going to call it the Hummingbird from now on, to make that a little bit easier. And it's a miniature portable liquid separation system that we feel is perfectly applicable to point of sample types analysis. So I'll step through the detail of that technology and focus on the configuration and how we've approached the opportunity. But importantly for this session is then to focus on the work of one of the graduate students on the PFAS analysis in soil. So as mentioned, the Hummingbird is fundamentally a framework based on the principles of capillary chromatography. And this is a collaboration that was born out of one of the industrial transformation training centres, Aztec, in a collaboration with the University of Tasmania. And the technology came about because we were focusing on a gap in Pfizer's portable continuous miniature and modular manufacturing platform. And you can search that item on the net, and you'll be able to see quite a humorous video on the development of that platform. But the gap was, of course, that they didn't have an analytical technology to assess the performance of their reactions. And so we set about the design of a system that's here you can see embedded in a briefcase, and then ultimately to deploy the technology with the candidates from the training centre to demonstrate the performance of the technology in Pfizer's workflow. And continuing that development now to develop a fully fieldable version of the system for the applications in environmental analysis, which I'll touch on today. So fundamentally, the framework was around integrating application-specific modules. And it was the approach we took to this problem was not necessarily to compete with HPLC, but most importantly, be able to configure the system with the appropriate module to solve the problem. And in the case of Pfizer's work, it was their flexible API supply technologies research program. And their problem was that they needed something that was close to the reactor. And traditional HPLCs just didn't meet that need. But also they required the sensitivity of mass spectrometry. And in this case, we worked with the Microsaic electrospray ionization single quadrupole mass spectrometer. Now this mass spectrometer is based on MEMS technology. So the spray chip, the vacuum chip, and the quadrupole are all MEMS-based technology. So there's a very small vacuum chamber, which means the system is indeed can be sat inside a fume hood, and with the chromatography system sitting on top, we can now perform reaction monitoring. And in this case, the candidates focused on example of demonstrating 7 time points of the reaction, both in the UV absorbance as well as the mass spectrometry. And here the total ion current for monitoring the impurity, the active ingredient, and the starting material. So that was a very successful project. But there was something that intrigued us when we were packing up over the Christmas period at the end of 2019, in that Mohammed Hamida, the candidate, the PhD candidate, and I started at 11 a.m. packing up the Hummingbird and the Microsaic system. And we then travelled to our facility in Danbury and reinstalled the hardware and the mass spectrometer and had everything up and running by 6 o'clock early that evening. And that led both Mohammed and I to think about what's really possible in that portability, that whole fieldable nature, and the speed that we could pack and install the system to explore new opportunities. Well, you can see by that date, COVID intervened, and while our project is still progressing well in Groton, we couldn't leave the country. And in particular, nor could Mohammed. But that thought around the speed and the portability led him to look for opportunities in lockdown in Tasmania. And he set about to demonstrate how he could now deploy this technology into monitoring soil for PFAS analysis. And so in the image here, you can see he's set up both in a van or on the back of a utility, the full capability of monitoring based on a portable generator for his power source to drive the mass spectrometer, a voltage stabilizer, a D cylinder for nitrogen, and importantly, all of his devices, a battery operated balance and a handheld homogenizer, so that he could do the full workflow in the field. And this work was recently published in Analytical Chemistry in August. And I certainly encourage you to pick up the details of his work in that publication, as I'm not going to be able to give you the same thoroughness that the paper did. But moving on quickly, the configuration should look quite similar to what I showed earlier, so that we have the same idea of now assembling the different modules. These are syringe pumps that are driven through a master board and an onboard control. And then the integration with the Microsaic mass spectrometer through traditional column chromatography. And as I mentioned earlier, the nitrogen and portable generator being able to provide him the power. So Mohammed set about then demonstrating and optimizing the method for the separation of he chose 12 PFAS standards, and he's demonstrating here the cleanliness of the system. So the low background that he was able to demonstrate for each of the extracted ions for each of the different PFAS samples. And importantly then, that the chromatography gave him the separation times and the resolution that he was looking for to now start developing the methodology for the extraction of the PFAS from the soil. And so the second stage of the project was then to set about and demonstrate that he had a method that could easily be deployed into the field, and he focused on a gram of soil and then extracting that in methanol with this handheld ultrasonic workflow, and then filtering the sample and concentrating that under a stream of nitrogen so that he could make the measurements in the field. So importantly, of course, is in any of these type of screening approaches is to fully understand the matrix effect of the soil extraction. And he was able to demonstrate that, yes, indeed, there is that suppression across the board, but nevertheless, as a screening method, he was able to optimize the extraction and the separation methods to obviously give him the opportunity to explore the various concentrations of PFAS in the environment. As an initial sample, a classic extraction from a firefighting site, and the ability to detect the various concentrations of a range of different PFAS, and obviously the major PFOS firefighting foam dominating the spectra, and obviously demonstrating quite significant utility for real sample analysis in the field. To demonstrate how broad the opportunity was, he entered into a blind study on 10 different soil samples collected around Australia with a partner environmental laboratory. And all of this is, again, all of the data is published in the analytical chemistry publication. And it highlights the equivalent performance and sensitivity in the ppb range for the LC-MS in the laboratory and the field deployable electrospray ionization mass spectrometry, the Hummingbird ESI-MS approach. Very good correlation between the two workflows. Obviously some additional sensitivity in the laboratory, but overall the method detection limits were quite similar between the two approaches. And so this was really encouraging, and certainly from Trajan's perspective, an ideal opportunity now for us to explore in collaboration with the industry, where do we see this technology going? So in summary, this fieldable capillary electrospray ionization mass spectrometry for soil monitoring, I hope we've quickly demonstrated to you that the initial prototype performance of the Hummingbird with the little quadrupole suggests utility and rapid deployment. As demonstrated, we're able to move the system around quite easily. It doesn't have any of the requirements of traditional laboratory instruments when it comes to being able to deploy that in the field and use it, as you saw, in the back of a utility or in a van. Mohammed was able to demonstrate with more than 35 soil samples that all were extracted in the field using the Hummingbird ESI-MS system. And in comparison to the standard LC-MS methods, the Hummingbird demonstrated real-time utility as a rapid screening device, demonstrating very good sensitivity across the range from around 8 nanograms per gram for the PFOS and up to nearly the 3,000 nanograms for the PFXSA. So where does that leave us now? Where Trajan and the university are continuing to explore now opportunities of collaborating with the sector, in particular looking at working with the environmental consulting groups around managing the significant complexity and logistics of moving soil around, particularly big construction projects such as the Westgate Tunnel program in Melbourne, as well as everywhere around the world where you imagine there is significant challenges when it comes to moving tons of soil and containing and bunding, and then the subsequent analysis of all of those materials. With respect to the actual execution of this project, it's just my delight to be able to present the great work of the group. As I mentioned, this was a training centre, and Llewellyn and John and Mohammed were all candidates that had the opportunity to work in Pfizer to develop the technology, and then more recently with Mohammed's University of Tasmania colleagues to demonstrate the utility of the technology in the field in the PFAS analysis. Within the Trajan team, we have a significant software program, obviously supporting the development as well as engineering resource to lead the commercialization now of the technology so that we can start to deploy it into the field far more ubiquitously throughout Australia. And so very keen to hear any feedback and any interest from the audience around assessing and understanding the technology. But thanks again for the opportunity to present.